Section 2.5 is on transformations of functions. This should be a review from something you learned in Algebra 2. If you have a general function, we'll call it y equals f of x, and you add a number to that function, you're going to move the graph up that many units. And if you subtract a number from the original function, you're going to move the graph down. This is saying that we're adding and subtracting a number from the y-coordinate of every ordered pair on the function, because the y-axis is the one that goes up and down. If you add a number to the input, that's going to change the x values of the ordered pairs. That's going to move the graph left or right. In this specific case, it's going to move the graph left. But if you subtract a number from the original input, it's going to move the graph to the right. This is often the most switched transformation for students. They often confuse them because the plus sign makes you want to go in the positive x direction and the minus sign makes you want to go in the negative x direction, but that's not how it works. Another thing we learned was what happens if you multiply a function by a negative. That is going to flip the graph upside down. We have a phrase for that. We call it reflect over the x-axis. The last transformation that we're going to talk about is what happens when you multiply a function by a number. Well, if that number you multiply is bigger than 1, then the graph is going to get narrower. We call it stretch vertically, or you can say it gets narrower. But if that number you multiply by is between 0 and 1, so if it's 1/2 or 2/3, we are going to say that it shrinks vertically. You might best know it as the graph is getting wider. Now this is easier to do when you can show a graph. So here's an example that I did on Desmos. So I started by graphing y equals x squared, and that's the graph in red. That's the parent function. All the transformations will come off that parent function. The blue graph is y equals x squared plus 2, and you'll notice that that graph is the red graph, but shifted up 2 units. And then the green graph is y equals x squared minus 3, and you'll see that's the red graph, except it's been shifted down 3 units. Here are transformations left and right. The red graph is still the parent function. The blue graph, y equals x plus 2 squared, is the one that's been shifted 2 units to the left. And then the green graph, y equals x minus 3 squared, is the one that's been shifted 3 units to the right. Now let's do stretching and shrinking. So again, the red graph is the parent function. 3x squared, the blue graph, is the graph that has been vertically stretched or made narrower by a factor of 3. In other words, all the y coordinates of all the ordered pairs on the original graph were multiplied by 3. The green graph is wider than the red graph because it was being multiplied by 1/3. It was multiplying all the y coordinates by 1/3. And here's the graph that's been reflected over the x-axis. Well, now let's put it all together. So the parent function is still y equals x squared. But my new function is y equals negative 2, x plus 3 squared minus 4. So let's start with the easy stuff to talk about. The graph has clearly been shifted 3 units to the right. Sorry, that's the left. 3 units to the left. That's what this does. And then 4 units down. That's what this does. And because it's upside down, that's what the negative does. So it's been reflected over the x-axis. But there's one more transformation, and that is that 2. The 2 is independent of the negative. It does something completely different. The 2 makes the graph vertically stretch. In other words, it's narrower. So there are 4 different transformations on this curve. 3 left, 4 down, reflect over x-axis, and stretched vertically. You don't have to graph it to be able to tell what the transformations are going to be. Let me show you. I can tell you that if the parent function is x squared, then the 1/4 is being multiplied in front. It's a vertical shrink. The -4, that's going to move the graph to the right 4. Whatever's in the parentheses, because it's being added or subtracted from the input or x value, is always going to move the graph left or right. The +8 out here is actually being added to the output of the original function. So anything that gets added or subtracted from the output, y value, moves the graph up or down. This is going to go up 8. Now let's talk about actually taking a graph and moving it around. I'm not going to do all of these, I'm going to do some of them. But on this graph, that's just a general run-of-the-mill spiky graph, if I want to graph this, as long as you know that that's telling you to move the graph left 1, then all you have to do is take every dot on here. I would take all 5 of those, and you just move them to the left 1. And then you redraw the graph. All right. I'm going to skip B because we're not talking about horizontal stretching and shrinking. I'm going to go to this one. This one says move the graph right 2. So I'm going to take all my dots and I'm going to move them to the right 2. How about an up or down one? This one is down 2. So if I take all my dots and I move them down 2 tick marks, there you go. How about reflect over the x-axis? Reflecting over the x-axis, and I'll come back to that in a minute because we're going to talk about something called even and odd functions. Reflecting over the x-axis is just changing the y-coordinate. So whatever your ordered pair is, you're going to change the sign of the y component. I know it looks like I just wrote negative y. That's just code for change the sign of it. So this is at -2, 0. Well, you can't change the sign of 0, so that's going to stay where it's at. This ordered pair is at -1, 1. -1, 1, when I reflect it, is going to become -1, -1. Notice that all I did was change the sign of y. 0, 0 is not going to change because you can't change. 0 is not positive or negative. The next ordered pair here is 2, 2. It's going to become 2, -2. And then this one here is 4, 0. And when I switch y, I can't make 0 negative, so it stays the same. So you end up with a graph that looks like that. And now the fun one. F. How do I do 2g of x? 2g of x says to multiply all the y values by 2. So, here's my first order pair, -2, 0. When you multiply y by 2, you still get -2, 0. But the next order pair, -1, 1, when you multiply y by 2, you get -1, 2. And then 0, 0 stays the same. And then 2, 2 is going to become 2, 4 because you're multiplying the y coordinate by 0. And then 4, 0 is going to stay the same because 2 times 0 is 0. And there's your vertical stretch. There are two special types of functions. One's called even and one's called odd. An even function is a graph that can reflect itself over the y-axis. So here's the point 2, 3. Reflecting it over the y-axis means pretend like the y-axis is a mirror, and you're looking into that mirror. Where would your reflection lie on the other side of that axis? It might lie here. Well, that's at -2, 3. So notice what happened was that the x-coordinate changed signs. So an even function is one where if xy lies on the graph, so must -xy. Here's an example of a famous even function. Y equals x squared is an even function. Here's why. Well, 1, 1 is on the graph, and so is 1, -1, 1. It lies on the other side of the y-axis. Let's find another one. This is 2, 4. Well, then this better be -2, 4, which it is. And then 3, 9 is on the graph. There's another point on the other side. It better be at -3, 9. And it is. This is called an even function. An even function is one that's reflected over the y-axis. In other words, if you change the sign of the x-coordinate, but you don't do anything to the y-coordinate, that point also lies on the graph. An odd function is one that instead of reflecting it over a line, like an axis, you would instead reflect it over a point, the origin. Reflecting a point over another point is going to change the sign of both of those coordinates. So 2, 3 reflected over the origin is going to be at -2, -3. So xy is going to become -x, -y. Let me show you the most famous odd function. Y equals x cubed is the most famous odd function. Now, I want you to notice that the even function had an even power, and the odd function has an odd power. There are rules for longer equations, and we'll talk about that another time, but for right now, this odd function, I want you to notice that 1, 1 is on the graph. The -1, -1 better be on the graph, which it is. 2, 8 is on the graph. Then -2, -8 better also be on the graph, which it is. This is called an odd function. We can actually tell by an equation if the function is going to be odd or even. Now, you can graph it if you want. You can graph it and determine by the look of the graph if it looks like an even function, like it looks like it can be reflected over the y-axis, or if it looks like it's an odd function, if it looks like it could be reflected over the origin. But here's another trick. In A, f of x equals x cubed plus x, I want you to notice that both x's have an odd number as their power. When that happens, it's going to be an odd function. In B, I want you to notice 7 minus x to the 6th. The only term with an x is this one, and its power is even. It's an even function. In C, f of x equals 3x minus x cubed. Both x's have odd powers, so it's odd. And now for the tricky one. F of x equals 2x minus x squared. The first x has an odd power because its exponent is 1, but the second one has an even power. If that happens, then it is neither even nor odd. It doesn't have to be one of the two. It doesn't. And that is our section on transformations of functions.